It just saves to like your desktop or something?
Yeah.
Isn't it where you want to save?
Okay.
Yeah, I'm recording.
Cool.
All right.
So according to the state of California, do I have, no. Everybody's permission.
Yes, you have my permission. Although we had a security incident 3 years ago where someone did that without giving permission, and it ended up in a conference with everyone explaining the fact that you can't just record Zoom meetings without telling people you're recording Zoom meetings.
Yes, that is the law.
Yes.
Yep.
Okay. Well, so far we're not.
All right, let's bring this up. All right, so I got the data set up. I got that up. Does anyone want to share their screen?
Yeah, I'm pulling up. Pulling this up. The quarterly revenue. Okay. So it's probably, so this is the data set.
Mhm.
And so there's probably a couple of background things we want to go over. But let's look at the problem. And I've kind of been doing it. I'm not exactly sure entirely precisely what it's asking yet. But it says that there's a college and they've been doing some, they have a certain number of students who drop out after the first year. And this problem is basically to try to figure out if there's any sort of correlation between either incoming students' GPAs or whether they've taken the seminar or not to that impacts whether they're going to drop out or not. And they started doing the seminar in the hopes that people who took the seminar would then, fewer would drop out. There's a couple of things that are different here. And one is in this problem, we're going to break data up into different sets that are used for different purposes, and then also do something called logistic regression. So have you guys looked into either of these two things yet?
I haven't.
I have not.
Okay. I need to go find, I'll be right back. I'm gonna go get my my pencil so I can do my notes, my whiteboard thing. I gotta get my my writing pen. Okay.
Hello.
Hello.
Hi, sorry we're late. Is
Hey.
it on? He's on. Okay.
Just getting started.
Wait, why is this being recorded?
Being recorded? Yes. Don't sue us.
We thought you guys wanted it to be recorded.
We initially started recording partly to make sure you guys can rewatch whatever we discussed. But we actually just started, so.
Oh, okay. We're just in time for the recording.
Exactly. So a lot of times when you are designing models, you have a large data set. And what people will typically do is break it up into 3 parts. There's training, there's validation. And sorry, I can't really write all that well with this pen. It's not an Apple pen. It's just it's like staticky thing. Validation, and then there's a test set. And kind of a standard way of breaking this up is like 60, 20%, 20%. But if you have, for instance, like 1 million samples, you know, you may only keep like 100,000 samples or something for validation if you have much greater. But so training here is what you use to fit the data. So to come up with the parameters, this is what you come up with the parameters for the model. So this is where you're finding your beta 0, beta 1, beta 2. And then your validation data. This is what you do this is the part of the data set that you use to choose a model. And then the test is your final one to generate accuracy. And that doesn't look at all like the word accuracy. Let's use capitals. Okay. Basically what's going on here is you want to make sure that your data, that your model is accurate and doesn't overfit. Doesn't overfit data, and that it doesn't have biases. So when you're testing different models, like for instance, if we go back to when in some of the prior problems, like the car one, you know, we tried a model with we did a model actually with the repair shop. We did a model with people, we did a model with type, and we did a model with months. And it turns out that if you want to really get good, comparisons of models, it's best that you don't train and choose and tune your models on the same data set. It's best if you use different data sets. And the goal of that is because then it removes any bias that you might have in the data. And what happens there is that, so you have your train, you have your validation, and then you have your test. So, and then you have here, you have an error or an accuracy. So, actually, I'm gonna delete this here. So if you plot your percent error on your actually accuracy, boy, this pen really sucks for writing. You might find that if you find your accuracy on your training set is, you know, approaching 100%, but your validation and your test data are low, like in this region, you may have done something called overfit the data, which means that you picked a model that predicts this set of data very well, but it doesn't predict this set of data very well. And the way to think about it is, imagine you have a data set that looks something like this. Okay, so imagine somehow you have some sort of data set with dependent on two variables, x1 and x2. And you have two different things it could be. It could be this, which is type A, or it could be this, which is type B. All the purples are meant to be the same thing. So a good model you might expect to look something like this, where you kind of draw a line, a circle around these. And so everything inside the circle could be A, everything outside the circle could be B. And maybe this isn't, let me go ahead and just get rid of some of these inside of here. Okay, so we have most of the B's are on the outside. Some of the B's are on the inside. But, you know, just conceptually speaking here, like you may have developed a model that accurately detects A by drawing some sort of a boundary curve around things like this red line. But if you kept adding like number of parameters that you're testing, for instance, you might get it to the point where you develop a model that essentially does this and is super specific and really rejects all of these purple things. And you make this really weird shape here, which you can imagine if you had like your x1 plus x2 squared plus x3 cubed plus x4 to the fourth plus something. You really develop like a very high order equation. You could develop a curve that looks like that. And this type of a curve here might give you 100% fit on your training data. But if you go to test it on your validation data or your test data, it may not fit very well at all because you really didn't draw something that learned, that fit the data. You learned something, you developed something that essentially memorized the data. And that's not what you consider to be necessarily a good fit. And so the way you go about kind of making sure that you have a good model that's generalized to the population that you're trying to predict is that you break it up into these three pieces: the training piece, the validation piece, and the test piece, so that you can force it to generalize like this red thing instead of overfitting it and adding in biases like this pink thing. And this is just kind of, you know, something that is accepted about data science, and I'm sure I could do a better job of explaining it. But this, you know, essentially when we were looking at before the other problem the other day, where there was one that was an, you know, 85%, but it had a bad variable, and another one that was 90%, that seemed to be a better fit. and I was saying choose this one because I like the model better, even though this one here had a higher accuracy. You know, you might be able to show maybe that it had a higher accuracy because it overfit the data a little bit better. And if you would generalize that and tested it on another data set, its accuracy may have been lower. So you split data sets up into 3 pieces then. One is to train, to actually develop these parameters here. The second is to validate or choose the model. And that's where, if you were trying to pick whether you wanted to do an equation of beta 0 plus x1 or beta 0 plus x1 plus x2, sorry, there's actually betas in there. Beta 0 plus beta 1 x1 plus beta 2 x2. So here's model number 1 maybe. Here's model number 2. You would pick those model using this portion of the data, this validation portion of the data. You would pick which model maybe gave you the best accuracy out of that. Trying to think of an example. Let's come back to this. There are reasons when you want to use the validation, and it. Oh! I know the validation. We'll come back to logistic regression, but in logistic regression, you might want to tune the cutoff value. So there's something called the cutoff value, and that's what you would use to pick on the validation set. That's what you would use the validation set to choose. So we'll come back to that later because it'll be a better example. And then the test is your test data set that you use to generate accuracy. So a lot of times when you're doing data competitions, or if you're doing medical device testing or something, you'll have 2 different populations. One is your training set of population, and the other is your test set of population, and you keep them separate. So when you're trying to do a competition of data, generally you don't have access to the test data set. And if you're trying to develop study models using clinical data, you don't want to train and test your, you don't want to train on your test data. The FDA won't let you do that because you'll end up just creating something that works well on the test data, but doesn't actually generalize well to the population. So I know I've kind of said a lot here, and I don't know if I've said it clearly, but does it make sense why you split these things up into 3 pieces, or at least what the 3 different parts are?
Yes, I think so.
Okay. We'll come back to validation here in a bit. And it is part of the problem, the homework problem. And the validation is going to be useful when we're talking about the cutoff here. So now the next thing we're going to do is something called logistic regression. So linear regression is used for continuous variables. Like 1, 1.2, 7, 8.9, 3, etc. Right? So we know how to pick, we know how to choose. Let's say you have some y is going to be some function of xi, which is going to equal to, you know, your beta 0 x, your beta I xi, some whatever, however many of these terms you have. So it turns out that, you know, let's say you want to do something that is not a continuous variable. So in the case of the homework problem, it's drop class. You know, or what is the probability that if you earn over 100,000, that you have a master's? You know, so there's a whole set of prediction of predictions that you can do on these categorical variables. And the way that you do that is through something called logistic regression. Okay. And this one here looks fundamentally different in that the way you're now kind of doing it based off of these probabilities. So what's the probability that if I have, and let me see if I can see it in the book, so I can use the same terminology that they do. Yeah, it's essentially, do I predict, I predict that something is a particular category, I guess. So predict variable here. And I can say that if my probability is greater than 0.5, it is type 1. Or if my category is less than 0.5, then it is not 1. So I guess, using kind of the general examples, let's say you want to predict whether something is a cat or not, or a dropout. You can use logistic regression to say whether something is a cat or whether something is not a cat. That's what the exclamation point means, not cat. This right here, this is the cutoff variable that we were talking about before in this logistic regression to tune the cutoff value. And when you're developing these probabilities, you can change actually where you want to draw the line on what you accept. And this value here can be between 0 and 1. So the way this math works is and I'm going over this because I bet, based off of the last quiz, this is something he's going to ask about. So let's say this is our x-axis here. And this is our y-axis. And in linear regression, when you go to solve an equation, let's say you have, for a set of x's, you have a bunch of things up here. And for another set of x's, you have a bunch of things down here. Well, what linear regression does is linear regression will fit a line in between these points. And if you're trying to fit a 0 or a 1, this doesn't really make sense, you know, because first, linear regression is a line. So it's not like it's, you know, below this x1 right here, below this point where it crosses, you want this thing to be 0. And above this part here where it crosses, you want this thing to be 1. And this general line that we talk about doesn't fit very well, because once you get past this point, all of this here, you know, it's not stuck at 0 anymore. It's going to a negative value. And up here, it's once it hits 1, it keeps going to a positive value. So for predicting categories, linear regression doesn't do a good job. So it turns out that there's a whole different set of equations that you can use, which is essentially what's used in logistic regression. And that is, it uses exponents. And this is the equation that it uses. Not really going to ask, or I don't think we're going to talk about how this is derived or what it, or necessarily how it works, but it works essentially the same way that linear regression did, is that somewhere there's a function that you're trying to minimize. And this theta here, I wrote it in shorthand, is actually, this is the equations that we were used to before. So, you know, when we go through and solve these equations, we're going to get these beta 1, beta 2, beta 3 like we did before, except they're going to get plugged into this equation. And if it looks nasty, it's because it kind of is. But do you guys remember exponents? Did you ever do, or this E right here? Did you guys ever do natural logarithms and the exponential?
Long time ago.
Long time ago. Okay. So let's remember a couple of things, right? There's a couple of things we want to remember. One is that, so E, so any number to the 0th power is equal to 1. You remember that?
Mhm.
Okay. And 1 over 0 is equal to, well, it's undefined.
Mhm.
And 1 over infinity is equal to 0, right?
Mhm.
So basically, if you divide a number by 0, it starts getting undefined. And the smaller 0 gets, the larger the actual number becomes. And if you divide a number by infinity, it becomes 0.
Mhm.
So let's look at this right here and plot it on this chart right here. And again, the reason I'm explaining this is because based off his last quiz, this seems like a quiz question he's going to ask. So let's just use the basic case of let's just look at theta right here and use the case for when theta is equal to 0. So when theta is equal to 0, we have 1 over 1 plus, and e to the 0 is, any number to the 0 is 1. So that's 1 over 1 plus 1, which is equal to 1/2. Right here. Okay, so that's neat. we have a 1 here. We know that this value is 1. We know that right on here, this value is 0. And for the first part that we're looking at, when this theta thing is equal to 0, we're right in between 1 and 0. So that's neat. So let's look at what happens to the number when x starts getting really big. So as this theta, so you have these numbers here, you have these x's, and let's say that x's are starting to get big, going to infinity. You have 1 over 1 plus e to the negative infinity. And let's remember that x to the negative power is equal to 1 over x to that power. So this here then, 1 over 1 plus e to the negative infinity is 1 over 1 plus 1 over e to the infinity. E to the infinity is infinity. 1 over infinity is 0. So this is equal to 1 over 1 plus 0, which is equal to 1. So as x gets bigger, this probability right here, as this theta gets bigger, which is our x is getting bigger, this number here approaches 1. So it kind of does this. And let's look at when x goes to negative infinity, and we're plugging it in here. So we have 1 over 1 plus e, the negative infinity, which is equal to 1 over 1 plus these negatives cancel out, e to the infinity, which is equal to 1 over e to the infinity, which is equal to 0. So now with this equation right here, you have that as x gets smaller and smaller, our number here approaches 0 and gets close to 0. So here, you can see that, without understanding any of the underlying math, that these probabilities with this equation here do in fact float between 1 and 0, with the probability in the middle being, here being 1/2. And that 1/2 there, this is our cutoff, which, as we talked about earlier, you can kind of change. You can move it between 0.5 or 1. And all that does is it just has the impact of taking this whole thing right here and shifting it to the right or shifting it to the left. So let's say your curve, if your cutoff is 0.5, you're going to have your standard thing that looks like this. If it's 0.1, then your curve is going to look like this. You're just going to take this guy here and shift it to the right, shift it to the left. But conceptually, this is kind of what's going on with cutoffs and with these equations. So there's an interesting side effect then to logistic regression. And that is that, as we can kind of see from the way these tables are built here, of having a probability greater than some number and it's equal to some object, and if it's not that number, it's less than an object, is you now start to get into false positives and false negatives. And we had the same thing when we were doing hypothesis testing, I think it was. No, not hypothesis testing. Earlier in the statistics, when we were doing, I forgot. Anyway, so now you start to have the possibility of an actual and a predicted, where you can actually have something that isn't, something that is X, and it is X, and you predict that it's going to be X. So these are your, these here are going to be your true positives. And so this is when actual is 1, predicted is 1. I might have it backwards to what the book does. They might do 0 first. I don't remember. Anyway, and here you have 0 and 0. So when you think it's going to be 1 and you predict it's 1, you have a true positive. If you predict 0 and it is actually 0, you have a true negative. If you predict it's going to be 1, you predict 1, but it is actually 0, that is a false positive. And if you predict it is going to be 0, but it is actually 1, then you have a false negative. And this here is called a confusion matrix. And your number of true positives plus true negatives plus false positives plus false negatives is equal to the total number of samples in your data set. Okay, so ultimately, when we're doing these logistic regressions, we're categorizing, we're predicting a logical variable. We are using some math, particularly this function here, to figure out whether it's 0 or 1. We select a cutoff value of where we're going to draw the line, that if we say, if I'm 50% sure it's a 1, if I'm 20% sure it's a 1, and then you're going to get these sets of this confusion matrix out, where you can see like the number of times you were correct with the true positive or true negative, and then the number of times you were wrong. And now the process of comparing comparing models is now based off of the breakdown in here, where the things fit. Okay, so I'm sure I've done a horrible job explaining all of this, but it's something good to keep in mind while we look through the first problem. So any questions up to this point? Okay.
Mark, can you scroll down a little bit?
Yeah.
Okay, thanks.
And I'll give you all, so A, this is recorded, and B, I can give you the PDF for this too. So I think that there takes us through chapter 9, section 9.1, 9.2, and 9.3.
Mark, this is very similar to the error matrix, right? The confusion matrix.
It is. Yeah, conceptually they're identical. In fact, I'm quite sure that they are you guys seeing my screen?
Yeah.
You're seeing the book, right?
Mhm.
Okay. It doesn't have the green box for me, so I just couldn't tell what you were saying. Yeah, so I'm sure that that the two are related. That the
From what I remember, it seems to be flipped.
yeah, you know, I think you're right. I think it is. You put the 0 in the upper left-hand corner and the 1 in the
Yeah.
right-hand corner. Yeah.
Yeah.
I'm
'Cause
sure the
I
names
remember-
are the same, but yeah, I completely got that. Yeah, I think you're right.
Because I remember the top left quadrant is like type 1 error, and then the bottom right quadrant is type 2 error.
Yeah. Yeah, I think you're right on that. Um, oh, right, the arrows under the curve. Yeah, error, actual class. Yeah, I did that backwards. Yeah, predicted class, actual, and predicted. Yeah. Okay. So now let's look at the homework problems and apply the theory. Oh. Is there a faster way to do this in Excel? There's a way that I can list all sheets, right? There we go. No, it's not faster. Okay. Boy. Okay, bear with me while I delete these. If I were doing real video editing, this all would be removed.
Mark, I don't know about Mac, but I know if you shift or control and click on the windows, you can delete all at once.
I tried that on the first one. It didn't do all of them. Oh, okay. Thank you. I guess I didn't do it right the first time. All right. Okay, so here we have a data set. We have student, drop, GPA, seminar, partition. Okay, so in the problems, for 7, okay, so it says evaluate the candidate logistic regression models based on their predicted performance on the validation set. Okay, so student here, this first column, it's unique. So we're just going to ignore it, right? The dropped is what we want to predict. And I changed the order. I moved dropped to be in the second column. It's actually wasn't necessary to do, but that's what I did. Partition right here has T's and V's. This is the column that we're going to use to determine whether something's in the training set or in the validation set. So the way you go about running this is you come over here to, you have to use solver for it. You're using data mining. You're going to do classify and logistic regression. Okay. So now we're using worksheet last year. We're going to use our data set is from A1 all the way to A501. And so some of the neat things now about Solver is that when you go to do this, it already has found the various things in the data that can be variables. And I've already selected this, so I'm going to go ahead and bring them back. Okay, so I have here, we have student, dropped, GPA, and seminar. And for some reason, when I click on different things, they disappear. So let's keep that in mind. So student, yeah, when you click on it, it disappears. I don't know why. Student is not a useful data, is not a useful variable for us. Dropped right here is going to be our output variable. So we're going to add it. So dropped goes into our output variable. So this is one of the differences between solver and kind of the logistic, the data linear regression model thing, is that solver actually, instead of calling it dependent and independent variables, it actually has an output variable that you select. And we're putting dropped here. That's the one we want to predict. We're not using weights. Maybe we'll talk about those at different times, but you can weight the importance of these variables in the same way that we were able to weight like the 5 forces analysis from Porter. It's the exact same concept, just weights that you throw in front of everything. And so the first model we're going to do is we're going to do it based off of GPA. We have logical variables, which will be listed under categorical variables. In this particular case, our categorical variable would be seminar, for instance. And then continuous variables go under the selected variables. And we're going to put GPA in there. So the first model we're going to run, we have 2 classes. We have GPA input. We're only using the GPA to predict the output variable. The output variable is dropped. Our success class is a 0 or a 1. We're picking 1. We were talking about the probability cutoff. This is where you set that value right there.
Hey Mark, real
yeah.
quickly, mine is not showing the mine is not showing, you know how you have like the validation set and the training set? Mine is not showing that.
Your which is not, show me your screen so I know what you're talking about. Stop.
Hold on a second.
You can now do it.
All right, so it wasn't showing that in there. Maybe if I select it again.
Oh, okay. Yeah. Okay. Yeah, we'll get there. It'll do it in a second. So show me your main screen. Yeah, let's see that. Okay, so see how the data range?
Yeah.
Even though you selected all those fields, it didn't put it into here. You have to change the data range from A1 to E501. See how it says D101?
Yeah.
You have to change it to E501. It did the same thing for me. It didn't actually care that I had selected all the data.
Oh, that's right. Okay.
Okay. Now for the validation set, so we can go ahead and continue to use yours. Yeah, you can't change those. So send the GPA to the selected variable. Okay, send drop to the output variable. Okay. And now everything else is the same. Now hit next. Okay. So in the upper left-hand corner there's partition data. Click on that. Now say yes, partition data. And now we're not going to do the random partition. So Solver will automatically go through your data and select, randomize it. And here, yeah, we're going to use the partition field and say done. Now it will have, now it'll have everything. And now in the, go ahead in those lower boxes, in statistics and advanced, just click everything. I always add it all. Okay, next, go to next. And then go ahead and do detailed report, although I don't know, yeah, score validation data, summary, lift charts, and detailed reports. Just collect everything. Okay, and now say finish.
Do I want to do it?
Oh, no, you want to keep the first row contains headers.
Okay.
Yeah.
Finish?
Yep.
Ooh, what does that say?
I don't know. Say okay. I have no idea what that is doing. Mine doesn't have the
Let me
third
try this
box.
again.
Yeah. I think if you just do it again, I think something happened when,
Try this again.
yeah. Okay. So partition data, same thing. I have my partition data, use partition variable, partition. So you can, if you use random partitions, you can set a seed value. And the nice thing about setting a seed value is every time you run it, then it will select the same, it'll do it the same way. Here is where, for instance, if you want to do a split 60, 20, 20, you would set that here. You would if it let me. Oh, user defined, sorry. Yeah, you go user defined, 20, 20. Okay, so you can change it if it's user defined. We would do automatic, but here we're actually just using this partition variable, which sets it specifically. Partition done. I selected everything. Yeah, again on mine it doesn't actually show the. Some things aren't shown, which I don't know why it's doing that. Like it doesn't say training data and validation data up here. But I went ahead and selected everything, and I hit finish. And now it's going to go through and model. Okay. So here we have our logistic regression output. All right. Okay. So now Solver gave us a whole bunch of tabs, and there's a whole bunch of information in it. In there, we have how many iterations it did. We have some stuff about the error, the R squared. First thing we're going to do is we're going to look at these coefficients. And so just like before, here we have our intercept coefficient and our GPA coefficient. And if we look at his example problem, he said to keep us on target, the model with the GPA is 0.375 minus 0.633. Here you have negative 0.375 and negative 0.633. And then just to be clear, to come back to something that we did earlier, those values that we saw plug in to this equation right here. So our probability, if you're going to do a predict for this first one, is 1 over 1 plus e to the negative, and it was 0.375 minus.
Mark, do you want to do you want me to turn this off, or do you want to do a double share? What do you? I know you're marking something up.
Yeah, turn yours off. I think you should see my screen if you stop sharing.
Okay. All right, there we go. Yeah.
So this here is the equation. If you were going to calculate individual probability estimates, you would put it into this equation where this x, in this particular example that we're doing, is your GPA. And in Excel, if we were going to do that, so I'm going to do B0 is equal to negative 0.375. Oh, actually, B0, B1. This is equal to that. Okay, so if we predict here, the equation is equal to 1 over 1, 1 plus E XP. And then the number is negative 1 times 0.375 minus 0.633. Actually, we're going to do is equal to negative 1 times M2, which is our B0, plus our GPA, which is C2, times our B1, which is M3. Yes, go ahead and correct it. And then the other thing I also wanted to do is I want to make sure that these fields don't change. Okay, so the first value then here, if we're predicting whether or not they dropped, we said here the we had a value of 0.177, so they did not drop. So that's good. Our prediction is less than 5. We said no drop. We come over here to the training score, and if we look here, so this is the first record, the drop to 0, and we look at the post probability 1 of 0.1172. This should match this value, 0.1172. In fact, if we copy this a bunch of times, that's not right. Huh, that's really weird. It's copying the value and not the, that's really strange. All right, I just had it update them now. Okay, so the next one was 0.159, 0.209, 0.167. Okay, so 0.159, 0.209, 0.159, 0.209, 0.167, 0.182, 0.167, 0.182. Okay, wonderful. So now you can see kind of how you go about actually hand calculating these and how they correspond to these fields that come out. I think one of the things about using Solver is that now Solver completely abstracts all of this from you, and you don't actually have to go through and do any of this by hand anymore. You can just read the outputs from Solver. So let's go look at that confusion matrix, because that's really what we care about. And don't forget, there's these p-values, you know, like we had before for each of the individual ones. So the intercept is a p-value of 0.7. It means the same thing. We're not really sure if the p-value is 0 or not. You know, here we have that the base GPA is apparently, or the base probability of dropping appears to be 0.375. Well, it's not really the base probability of dropping, because this is an exponent. It's that first beta 0 term. So these don't mean what they used to in the linear world anymore. This doesn't mean that 0.375 of that 0.375 is the base GPA. It now has, these are pure coefficients, I think, that are divorced from that are divorced from the linear explanation that we were able to give before with linear regression. Because you could say, you know, when GPA goes up by 1, that the Y value goes up by 1. But here, when the GPA, for every point of the GPA increase, you know, that exponent decreases by negative 0.0633, and it's a negative exponent. There's no good translation of that back into human language, I think, of what these variables are doing to the predicted Y value. But you can say that GPA here is decreasing the value of the exponent, which means that it is decreasing the value of a negative. So it's pushing that negative small, wait, hold on. It's pushing that negative, it's making that negative bigger. Sorry. The minus 0.633 is making that exponent smaller, which means the exponent is becoming bigger, which drives the value closer to 0, which drives the probability closer to 1. Well, anyway. Okay, so now we got to come in here and look at our training score. So here we have in our actual and predicted matrix, in our confusion matrix, we have the actually 0 and found to be 0 were 241. And things that were actually 0 that were predicted to be 1, there were none of them. Things that were actually 1 and predicted to be 1 were 0. And things that were actually 1 but predicted to be 0 were 59. So basically what our model did is our model turned everything into somebody who was not going to drop. And here's what's really neat about that is our model apparently didn't work at all. It didn't do anything. It just marked everything as 0. And in fact, if we come in here and we look at our probabilities, you know, you can kind of see that all the red ones were things that were incorrectly categorized. And you can see we never got a number above 0.5. So like it just simply never categorized anything correctly at all. So it just simply predicted that nobody dropped. And now here's, look at this. It was 80% accurate. It was 80% accurate by not doing any work at all. And this here, you know, kind of is one of those things that highlights that there's not one variable that you can use generally to see whether something, a model, is a good model and whether it's working. Because if you only rely on the accuracy, you'll see that here's an 80% accurate number. Like it's completely garbage. We can see it from the result. It's a completely garbage number. but it's 80% accurate. So when you look into this, then you have to start thinking about other parameters. I mean, one is look at that. Definitely look at the confusion matrix and see what it tells you. There's something else that's interesting here. Here you have these things called specificity and sensitivity, or precision and recall. Now, these numbers here are described in the book, these performance measures. And they have, there's these things called lift charts and these, lift charts and the ROC curve. Unfortunately on mine, the ROC curve didn't show up. So let's see, how do you talk about this here? So sensitivity or recall. So one of them is basically one of them is if I have, let's say I have a data set with 10 dogs, and I ask, how many dogs do I have in this data set? And I return a list of 10 items. So one of these, which is the sensitivity, I think, is hold on a sec. Sensitivity is N11. So sensitivity is how many of the actual things in the set that I returned versus how many of them were there actually. So if I had 10 dogs in the data set, did I in fact return the 10 dogs from that data set? That's sensitivity, I think. And then specificity is, of the 10 items that I found for you, how many of them in fact were dogs? So they're kind of two different numbers. That's the way I remember them being. This is one area where I'm going to have to go and read up again because I don't really remember it well enough to explain. But what I do remember is that things on this line are bad. If you're on the line, it means you can't tell the difference between something that is in the set and something that is not in the set. What you really want is you really want a curve you want a curve that comes up here. That is kind of hugging this part. You want something with good sensitivity and good specificity. This ROC curve kind of tells you where you are. You want to be as far away from this line as possible, basically. Let's see what I got my mouse. Okay. So I think, yeah, somewhere in here, when you look at this precision and this F1 score, you see that we didn't actually get anything. So I think even though the model is 80% accurate, it's not a good model. So there's a few other things we could do here. We could try changing the cutoff value, for instance. See if that does anything. See if we can find a good spot. This one here is 0.23, 0.24. No. Let's just go ahead and try it. Just see what happens. Come up here. Data mining. Classify. Logistic regression. change my success probability. Everything else is going to be the same. Okay. And so now what happens is that
Mark, what did you
Solver-
change it to?
I changed it to 0.2.
Okay.
So Solver outputs now a whole new set of sheets. So the original ones are over here. So let's look at the new ones, see what happens. We should see a change. Okay. So here you can see by changing the cutoff value now, I actually changed the number of false positive and false negatives. And now we have a model with lower accuracy. And now we have specificity and sensitivity and precision and an F1 score. Okay. So now we have the fun part of actually doing this a bunch of times now to see if we get a better model that predicts things. So first, I'm going to go ahead and go back to the problem where it said here that we have an observation with the GPA and whether they enrolled in the seminar. So Dana College has a 1 hour long seminar to help first year students. And they want to see if the seminars have a positive effect on retention. And Dana's administration also suspects that students with lower school GPAs have a higher probability. So we just did one with the GPA. Now we're going to do one with, see if they've attended the seminar or not. So we're going to come back to data mining, predict, classifying, logistic regression. Now, to add in a seminar, we're just going to click on seminar and add it to our categorical variable. Now we have GPA. We have categorical variable of seminar. Still no weight, dropped. You can remove GPA from the model. So we'll go ahead and do that. I'm going to put the success probability back to 0.5. And then I'm going to do it one more time. Put GPA back in. So we have GPA, seminar, success probability 0.5. Okay, so now we have 4 models here. We have our first model. Well, this gets. Do you know how to see all the sheets? Can you get a list of sheets that are open?
I thought it was like you can right click, but is it not there?
If I right click, not. No. Let's try shift.
If if you do like move or copy the names of them, but like
I can't just, yeah, I just wanted to see a list. Oh, well. Okay, well, we'll come over here. Let's go look at our validation score. So this is one.
Mark, are you getting under your log, your output 3? Are you getting two as two session values? I'm getting one that's a redded out session value for some reason under the first tab.
Am I getting a red a session? Where am I looking?
All the way at the bottom for your coefficients. Yeah, okay, you're getting the same thing I am. Okay.
Yeah. Yeah, so I think that means that it didn't use there's only two categories of this variable, this categorical variable, 0 or 1. So I don't think it needs to use both 0 and 1. I think if you were to, this is the case where the coefficients are going to be n minus 1. So if you had three categories, it'd probably be a seminar 0, a seminar 1, and a seminar 2. With the seminar 1 and 0 being used, but not the seminar 2, is my guess. Yeah. Okay, so on our first one here, we have an accuracy of no. Training charts, validation summary. Okay, so this is the one where we used, I think we used GPA and the drop class. So prediction drops, shoot, I don't remember what we used.
So I just did a quick walkthrough and it doesn't seem like any of these propagate a more balanced confusion matrix. They're all heavily weighted into the 0, and the 0, 1s.
Yeah, they're all, they just classify everything as didn't drop, right?
Yeah.
So this is now gets to be to the second part of the problem, which I haven't done, which is that they realized they jumped directly without exploring the data. So now we have to see if we could figure it out why the data isn't good. So now we're going to need to do something that we did before.
Like if we slowly dial back that probability rating.
Yeah, but yeah, so we can definitely do that. You can just keep rerunning the classification diagram until we get an accuracy that we like. But let's actually look at the data and see what's happening here. So we have dropped versus GPA. Let's do a scatter plot. Probably want switch row. Oh. X values. C Okay. Um,
Looks like two worms racing against each other.
yeah, it does, doesn't it? I mean, it looks like if you're going to drop, you do tend to have a lower GPA, but it's not a requirement. Like nobody with a GPA higher than 3.5 dropped. And let's look at, oh geez. How would we do this? Well, we can look at drop versus seminar. No, that's not going to do any good at all. Oh, you know what?
It might.
Yeah, it might. I was thinking this is this begins to be a perfect time for a pivot, isn't it? Isn't this what pivot charts were made for?
Maybe.
Sure.
If I want to count.
If I learned anything last week, it's pivot charts are awesome for everything.
All right, let's do a pivot chart. How do we? Where's pivot chart? Here it is. Pivot. Select the table or range. B to D. Okay. Put it in the new one. Build a pivot chart. Okay. We want to look at dropped and seminar. Now values of this and that.
Yeah, so you got 98 dropped and 111 seminar.
Yeah. So if I want to put I want some of drop, some of seminar.
So the bolder one is seminar and the subcategory is the dropped.
Yeah, so what I want to do is I want to know how many dropped who took the seminar and how many dropped who didn't take the seminar, right? So I want like drop.
Would you want it in column instead then?
Yeah, that's what I'm.
So you just drag maybe the drop. Yeah, there you go.
Values and seminar here.
No, you would just leave the seminar in the row.
Okay.
Oh, you might need to bring it back. Because right now you have it in the values.
So I want seminar here.
Sure, either or.
So some have dropped. I don't get. Sorry, I still don't get these stupid things.
So take one of the value, one of the
Oh.
column, and put it into row. So then you
Oh, I see what you mean.
Yeah.
Drop and seminar. Okay.
You might want to move your chart because it's blocking your table.
Yeah. Okay. Just it's now when you hear some have dropped.
And we're only looking at those who took the seminar and dropped, right? Not all that dropped and all that didn't take the seminar, right?
Yeah. Can you do this part? For the-
So the seminar is on the rows, right? And then you have the, oh, why does it say that? Series and categories. Oh, can you click on the pivot table?
Yeah.
Okay, there we go. Now it's back to the rows and columns. I was like, wait. So yeah, the row you have seminar. So you have the 0, which is they took the seminar.
Yeah. No, 0 is they did not.
Did not. Sorry. 0 is they did not, and then 1 is they did. So that's the they did not is the first row all the way across, and then they did is all the way across on the second row.
So 79 dropped who did not,
Take the seminar.
and then
Yeah.
19,
And 19 dropped, but that did take seminar.
19 dropped, it did take us, and then 92 did not drop.
Did not drop, but did take a seminar.
Yeah. Okay.
I mean, that's helpful right there. I mean, that's showing approximately that, you know, you're going from 80 dropouts to, you know, call it 20% dropout rate reduction if you take the seminar.
Well, 19 took the seminar, but still dropped.
Right. So you'd have like, so if you have 79 over, you know, whoever didn't take the seminar, that's the amount of, that's your dropout rate for people who didn't take the seminar. The total that didn't take the seminar, you know, under 79. And then for the seminar, I mean, it gives us at least some sort of a probability. It doesn't give us the regression line, but it does give us a probability about how effective the seminar is versus people who didn't take it.
Yeah. Did the some have dropped, some of seminar. Some have dropped, some of seminar. 209. Why are there only 209? Why aren't there 500?
There probably are ones where there were 0, 0. Actually, I don't know.
That should be in there though, right? Here we are.
No, well, they're not. Oh, you know what? Maybe we should not be using some. Wait, no.
Oh,
It should be count, right?
counting ones. We want to count, not a sum.
It might be the same thing though, right? I mean, just in this case.
Yeah, because it's 1 and 0s.
Can I
But someone in
count?
zeros.
Count have dropped. And seminar.
Yeah, well, actually, yeah, I will count the 0s.
There we go. Now we got it. Okay, so we have, these are how many drops. Count of dropped, count of seminar. Oh, geez. Do we really?
I feel like we just need to count one of the column.
Yeah, I guess maybe that's better. There we go. So 0 is dropped.
No, that one's seminar. So that zero is did not take seminar, and then the column is dropped
Oh, right.
or did not drop.
Did not take seminar.
Yeah.
Did not drop.
Yeah.
310 did not take the seminar, did not drop. 379 did not take the seminar, but did drop.
Yes.
Then there are those who did take the seminar and did not drop. And then those who took the seminar and those who dropped.
Yeah, so I think what we were saying earlier, or I think Ben was saying, if you did take seminar, then sounds like you would not drop. Look, I mean, the number is lower at least.
Take the seminar, you're less likely to drop.
Yeah.
Wait. No, the 19 is you did drop.
Took the seminar and still dropped.
Yeah.
Took the seminar and did not drop. Versus did not drop, dropped. So 402 didn't drop anyway.
Yeah.
Yeah. Okay. And so then we also know that people who had over a 3.5 or really over a 3.0 tended not to drop to begin with. So we probably want to do something where, like, you know, we segment the data even more, that if you're less than a 3.5, we don't count whether you were in the seminar or not. Maybe even less than a 3.0. Really, it's between this, if you're below a 2.5, you're going to drop anyway. So between a 2.5 and a 3.0, maybe, is where we care.
That's where the meat is. But how would we do that in the, how would we put that into the equation?
Well, I think they're saying that may explain the unsatisfactory results. And for next year's class, what could they do regarding the enrollment of seminars to better determine whether they have an effect on retention? I don't know. When we offer them to people between a 2.5 and a 3. I'm not sure, but yeah, this is essentially as far as I got the problem too.
Wait, is B only based on, I mean, can we look at the solver data?
Yeah. What do you want to look at?
Would the coefficient mean anything in this case? I mean,
For which one?
seminar, right?
Good point. GPA,
That p-value is super high.
p-value super high. Yeah. This was seminar and, oh, here we go. Seminar, GPA and seminar. It's not great. Okay, let's go look at I'll put 2, which is seminar only, not GPA. Well, seminar still is not great. This is the one where we changed the cutoff value. Yeah, and the cutoff value doesn't impact the p-value of any of these variables. If we look between these two here, see the p-values are the same. Yeah, so that was a very good observation that the p-value of the seminar, if you don't have any indication as to whether it helped or not.
Yeah, and the coefficient was like basically close to 0, so didn't. I'm not sure.
Oh, yeah. Might be able to, yeah, like maybe if we just narrowed in on 2.5 and geez, I don't know.
I mean, I understand why coefficient wise they would take out the 1 because if you're counting the 0, then you don't want to count the ones. But is there a way to kind of force the model to consider the 1 only? Because it seems like my understanding anyway of the problem is they're trying to understand whether the seminar is an intervention, right? Like whether that actually does help. And if we're evaluating 0, then that doesn't really help us because 0 isn't taking the seminar.
You could, so you want GPA and seminar, right?
Yeah, or at least having seminar, but not the case where seminar 1, they just zeroed it out because they're evaluating the effective 0 seminar. Like we want to know 1 seminar, right? Like 1 is having taken a seminar.
You could multiply seminar times GPA. You could do x1 times x2.
Oh, okay. Wait, but if you do that, then it's just the GPA, right? Because it's either 0 or GPA. Well, I don't. Is that what you mean?
I'm trying to think of how you would use that. Could try it, but I don't know. I mean, the bottom line may just be that It's not a good model. What would you use? So you're saying only use the seminar.
No, I'm saying the current model or the ones that we've been running, there is a coefficient for seminar 0, which is not taking the seminar. And I get mathematically why they would zero out the seminar 1 because you're already counting the seminar 0.
Oh, I see what you're saying.
Yeah, but I'm saying like the data is more interested in knowing the effects of the intervention, which is taking the seminar. So is there a way to really just look at seminar 1? Like we don't care about seminar 0, but we want to know what's the effect of seminar 1.
I mean, what's the effect of taking a seminar?
Exactly, yeah. I remember, wasn't it for the linear regression that whether you have the 1 or the 0, it just makes the coefficient negative or positive?
Yeah. This is what I'm trying to figure out how that works here, because that should be taken into account. Like this intercept here is already taking that into account.
Yeah.
And it's a negative. So as you take seminar 0, the value increases, which means that the negative gets bigger.
But is the relationship the same in logistics regression?
Well, in this particular case, it's all about it's all about what impact is it having on that theta equation. And
Okay.
when the seminar is 0, when you take the seminar, so GPA is making the God, this is all backwards. Hold on a second. Okay. So when it's 1, it's because that number gets bigger, 1 over E. When that number gets smaller, and that number turns more negative, then it starts dropping to 0. So I think maybe what's happening is that statistically taking the seminar isn't changing the value of the equation all that much. And the GPA does. So the other thing too is that only 92 seminar. 389 people didn't take the seminar. And 111 people did take the seminar. So I think the problem is this. Almost 80% of our data came from people who didn't take the seminar. And so this goes back to the point you were saying, Amy, in that most of our data comes from people who don't take the seminar, and so that's biasing that's biasing the impact that the seminar is having on the data. So it's like maybe we want to develop just a model only using the people who took the seminar.
Well, if you look at that, then it looks like 82, well, I did the math on the side, but 82% out of the people who did take seminar did not drop. I feel like that's too straightforward, so probably not the right answer.
Yeah. Well, the way I'm looking at, yeah, because I'm looking at, you have, does it say that they started a voluntary first year student, jumped directly into it without one. I don't know what's happening. Did not take the seminar. Did take the seminar. Did take, didn't drop. Did take, did drop. Didn't take, didn't drop. What's the ratio? What's the percent ratio difference? Can we pivot table? Here we have count of drops, field settings. Can we do a percent instead?
Yeah, I think you do the show data as, right? I think you just do the percent total.
Where's that? A grand total here?
Yeah. Or
That's fine. Oh no. No, it needs to be a percent of the row.
oh yeah, I was gonna say maybe you want to pick one of the values.
Yeah. Yeah.
You could do percent of row total.
Yeah. Field settings. Show that as percent of row total. There we go. So 80% didn't take it, 20% dropped. These are people who took the seminar. 82% didn't drop. 17% did drop.
Yeah, it doesn't look like there's much of a.
I'm sure if we did the margin of error thing, yeah, this looks like it's
like 3%.
it looks like it's the same number to me, right?
Yeah.
So what could they do next year to get better data? Maybe it's get more students to take it. There's just not enough. There's just not enough people who didn't take it, I think, to really.
Or we could tie it back to GPA and say that for the GPA where it was, you know, the most prevalent drop rate requires students within that GPA to take it.
Yeah.
Requires students between 2.5 to 3.0 GPA from high school to take the class.
Yeah. Or just make it mandatory, period.
Oh yeah, that's true. I mean, it depends how big their, you know,
Yeah.
school is.
Well, it's the year of COVID, so we know it's going to be an online course anyway. It scales.
Yeah.
So. Okay. Well.
So the thing is, though, I mean, this question, the only thing the log showed us during a, you know, logistic regression showed us that their data was wrong. That was the only thing that we got out of that. We didn't really get an answer out of that. It just showed us that their data was flawed.
Yeah, but we could. So I got to figure out where that ROC curve is. Maybe I just need to plot it myself. Decile lift gain. Oh God, I don't remember what these deciles are. Yeah. I'm gonna have to remember how to generate these lift charts. Somewhere in here, I think you can kind of.
I went through the chapter, and honestly, most of the other chapters have a step-by-step Excel kind of guide to walk you through the different, you know, how you get it in Excel. But chapter 9 was the only one that didn't kind of show you do this, then do this, then do this.
Yeah.
There on your, I'm just looking at the solver website for where the ROC curves are, and I think you just check those boxes which you did. And so supposedly if you click on log reg training lift chart and log reg validation lift chart tabs, you should see those curves. You have those tabs somewhere? Is it there?
Thought so. So log reg training lift.
Yeah.
Yeah, so for mine, when I clicked on that tab, it automatically generated it for me.
Where do you see it, Jimmy? Is it on the top, bottom?
So you know how we're in Excel right now? It actually pops up like the ASTM side of the graphs. And it, here, let me share my screen.
Are you using Windows?
Windows, yes. Can you guys see?
Oh.
Yep.
What?
Yeah, so I just clicked on the tab and it takes a couple, like maybe like 30 seconds and it just generates the.
Log reg training lift chart.
We can try this one. Let's see.
If
Did
you
you click the validation chart button?
Oops.
yeah, maybe if you click on those links, mark, like the chart, like those are you able to click on the hyperlinks on your?
Training charts.
Yeah, it just creates it. I didn't really do anything special.
Okay.
Wait, Jimmy, it just pops up.
Wait,
Yeah.
it just pops up?
It just pops up once I click on the tab.
Do you use the cloud app? Are you using the
Nope.
cloud mark?
No, I downloaded it inside. It's
Desktop?
enabled inside Excel. Yeah.
I do not see that. I'm in the lift chart right now.
Because there's a note on the solver website that also says to view these charts in the cloud app, you have to click on the charts icon on the ribbon apparently. But if you have the desktop, then that may not be the
Which chart icon?
problem. Charts icon on the ribbon.
Yeah, I see it. Okay, it's working. All right, I see it now.
What is it you do?
Yeah, I gotta click the charts and then I get the and then I get a, here you go, and then I can click on the ROC chart.
Can you show? Can you show us?
Yeah, let me show. Hold on. Okay, you guys see my screen?
Yep.
Yeah.
So if I just hit charts here. Oh, I gotta go to the lift chart. There we go.
You can change it.
Okay.
Chart and then RC chart.
Okay.
Oh, okay.
Validation charts.
Then let me go to the validation
Oh,
chart.
SL chart. ROC chart. Hey, all right. Okay.
There you go.
So I think here, I mean, this tells us right here, it's kind of only valid for this section here.
Yeah. Do this so
And
much.
then it separates.
Fitted. Optimum classifier is 1. Is the green. The random classifier, meaning just a random guess, is the red. And the blue.
That line, right? You don't want it to be on the red line.
No, you want it to be on the green line. See how the green is?
Oh,
Yeah, the green, the sensitivity and the specificity is perfect. That means that the number of items that you return. So if you have a data set with 10 dogs, that if you return 10 items, it means both that there are 10 dogs in the data set and you return 10 items, and that all 10 items that you returned are in fact dogs. So they're both, the sensitivity is 1 and the specificity is 1. So a good chart hugs those axes, that green line, as tight as possible.
okay. Well, the training chart definitely does that more than the validation chart.
So the training chart should, because that's the data that we're fitting. But you
Right.
don't want to, when you're trying to validate how good your model is, you don't want to test it on the same model that you trained with. You want to test it on the data that you didn't train with.
Yeah.
You expect that the test data looks better than the validation data. And when you're trying to pick a model, again, you're going to be picking that model and tuning it towards that validation set. So again, when you have a large enough data set, you really want to test against a different set than you trained and validated on. In this case, because we're only basically validation and testing is the same. So we're not tuning the model. We're not changing the parameters inside of it. There's a lot of parameters you can change. Inside of machine learning, there's things called learning rates that you can adjust. kind of like cut off, except for even more different. Well, thank you for the model thing. That's good to know how that works.
Are you using the cloud version?
I'm not. I'm using the desktop.
Oh, okay.
I wonder what it'll be different for the cloud because I'm using both. I got the I'm using the desktop on my PC, and then on my Mac. I thought I could use it on the desktop, but it turns out it just refuses to work. So I have to use it in the cloud.
I'm using it on the desktop in the Mac, on a Mac.
Mine is a cloud version, but it just basically is like an add-in on my Excel.
Yeah, it's the same thing I did on mine. I just use an add-in. What's weird, every time I close Excel and I open it back up, I have to like reselect the add-in for it to show up.
That's weird. Mine stays there.
Mine does
So-
not.
So one of the things that I've found out is it's because of the if you have a Microsoft 365 license, it works fine. But I don't have one of those. My work computer has a volume license. It doesn't have a Microsoft 365 license, so it won't work on it.
Then
And then
did you try to get the student edition from?
yeah, I did. And so the student edition, I talked to IT and it works on PC, but it won't work on Macs.
What?
The license is not approved for Macs according to them.
Really? That's
Yeah.
Because I think you need the 365 for the cloud.
Yeah, and so that only works on the website. So I try to do that. I have that on my Mac, like I can access the website. But when I installed it and tried to load the school license onto my Mac, it basically said something like you are unable to save using this version using this version or something like that on Mac. So it was really frustrating.
Oh, that's weird. Sorry to hear that.
Yeah, I mean I figured a workaround. It's just annoying.
All right. Well,
Should we call it? I mean, it's technically 11. It's technically 12:15.
yeah.
Oh, you're right.
Yeah, I was super tired.
Yeah.
All right. Yeah, I think it's time for us to call it night.
Yeah. Sorry, guys. About as good as I could do on this material.
No worries. I'm expecting. Honestly, I was reading through this, and I thought it was cool because I really thought, hey, this is going to give us, something to do in our future lives. But the chapter was just really dry on examples. I think it talked about theory a lot, so I paid attention to a lot of the theory, but it was like, again, well, how do you apply this?
So the problem is that, like, it gets the math that underlies. There's a lot more math that underlies this one than the linear regression. Linear regression, you can kind of visualize what's going on. These equations, I tried to kind of explain it using some other courses that I've taken. But it's much harder. I don't think I'm sharing my screen anymore, right?
No, you're not.
Yeah. So I took the machine learning course from Stanford last year, and so this is the logistic regression, and this kind of goes into the chart that I was trying to show, and the fitting this is a linear fit, you know, which isn't great. And then when you start to get more complicated, you know, you kind of start to draw decision boundaries that are circular. And then this here is one that's, you know, starts to get more fit. And so the ultimate problem is that when you're optimizing this, this is the equation ultimately that you're optimizing. So it's much more complicated than linear regression. So it's harder to explain for me. But in the end, like this is the equation that's in the book, right? Somewhere in here for logistic regression. Yeah, so in the logistic regression, they just say this. The function is 1 over 1 plus e and stuff. And here it's 1 over 1 plus e and stuff, where that stuff is this. Anyway, as you can see, it gets much more complicated. This is the cost function that you're trying to minimize. Like for linear regression, it was the sum of the square errors. Because this is a log chart, it really doesn't exist. Anyway, so the book just kind of skips all of that. And I think the reason why they skip it is because to explain it, you kind of have to start explaining all this. And it's really, I could do it if I had like another couple of weeks and thinking about it. But so I don't know if this is helping here at all. I think the book doesn't describe it because this is hard.
Yeah, I see alien language right here.
Yeah.
I feel like at least I know what this stuff is now. I mean, I don't know what it is, but I mean, we're doing the research for Tammy's class, and we came on a industry paper that had like a big old equation in there, and I didn't go like, "Oh, what the hell is that?" I went like, "Oh, that's just their equation to model the the revenue or the market generation." I'm like, I know what that is. I need to know what that is. I don't need to memorize that equation.
Yeah. I think that's the key here, is just to understand it's doing something. And I'm pretty sure that of the thing that he can ask us on the quiz is what happens basically as these things grow or shrink, which is what I talked about in the very beginning. Kind of how you find it at 1/2 at the middle and then 1 over here, 0 over here. But these coefficients really lose the translation to the real world.
The idea is that we can predict the dummy variable, right? Output. Like in a case of the example we walked through, if it's a 1, then yeah, they're gonna drop out. If it's a 0, then they're not gonna drop out. That's the predictability there.
That's right, yeah. So ultimately what you're doing is you're predicting the category, which is a dummy variable of a 1 or a 0.
Yep, makes sense to me.
This usually, I feel like, makes our lectures much more understandable.
Good.
Yeah.
Yes.
Yeah,
It'll probably
you
be
can keep
one of
up.
the- Just like last time where, the second time I go through with it, I'll be much more, it'll be much smoother because now I realize what it is I don't understand. So now I can go back and study up on that and understand it. So by Wednesday, I'll be pretty good again.
Or to Wednesday.
All right. I'll send you guys the PDF for this. And yeah, good luck to people who are listening to this on the recording.
Thanks everybody. Thanks, Mark.
Thank you.
Thank
Thanks, Mark.
you.
Thank you, Mike.